Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. So in the last lecture, we looked at electromagnetic waves, more specifically plane waves. And we looked at what happens when you substitute the plane waves into the Maxwell's equations. We saw that we get the dispersion relation. And after that, we looked at what the wave vector means and how the absorption happens in a medium. So in this lecture, we want to go forward from there. So we'll specifically talk about what are known as propagating and evanescent waves. So let's get started. So first of all, let us look at a plane wave. We've already considered plane waves. So plane waves are electromagnetic waves wherein in the direction perpendicular to the in the plane perpendicular to the direction of propagation, the phase is constant. So as the wave propagates, you have these alternating phase fronts that can be seen, right? And now what happens when such a plane wave is incident on a interface between, let's say, air and glass. So here I have two media. Let's say one is air. Let me use red. So this is air and let's say glass. These are semi-infinite media, and then there is an interface between them. Okay. On that interface, we have a plane wave incident. And for simplicity, let us assume that the direction of propagation is normal to the interface. So, well, I mean, the general equation for electromagnetic wave is already given here. And more specifically, if I consider an axis here, or rather, let me put an axis here, x and y. So it's propagating in the y direction, downwards. Okay. So in the air medium, where the refractive index is 1, we can define a wave vector k0. Let me use red for that. k0 equal to 2 pi by lambda naught, where lambda naught is a wave vector in air or free space. So now what will be the wave vector in the second medium, that is glass? So to understand that, we have to go back to the dispersion relation. So we already know that for the case of air, omega is c k0. Okay. Now when you go into the second medium from air, when the electromagnetic wave goes into the second medium, what happens to the wave vector in the second medium? We've already considered the solution of electromagnetic waves, right? So we said that in air, vacuum, you have the particular wave equation, and when you come to this, let's say any other refractive index, the speed reduces, the speed of the electromagnetic wave reduces. So what would happen is, let's say instead of c0, now my speed will become cn. Okay. So it might be tempting, when you look at the dispersion relation, we see that omega is ck0 or ck. So it might be tempting for us to say that the wave vector in the second medium also remains k0. And so this should lead to omega, which is omega, let's say in the medium, let's say omega g, which is this. Okay. Because after all, the dispersion relation tells you that omega is linearly proportional to k, right? So, but the problem with this approach is that omega, actually this is in fact wrong. We can't do this. The reason for that is omega frequency, right, is a property of the source. So I have an electromagnetic wave generated by, let's say, some source. There is a certain oscillation of the field. And just because that wave is incident on a medium, the frequency cannot change. Okay, the frequency is the same. So what changes? Well, to understand that, we have to consider, let's say omega, this is constant, and that is equal to the speed. Of course, we know that the speed reduces. So instead of c, this will be c of, let's say in this case, ng, because glass, right? And now what should happen to the wave vector? It has to be ng times k0. The wave vector has to increase. Okay. So this is a, let's say, k medium. Okay. When I have a wave incident on a second medium like this, the wave vector now becomes, the kg becomes, let me again go back to red. So kg is n times k0, or rather n medium times k0, okay, or in this case ng times k0. So what does it mean the wave vector increases? Okay, the wave vector is essentially given by kg 2 pi by lambda in the medium. So when we say that the k vector is increasing, we essentially mean that the wavelength in that particular medium has reduced. And this is what we will also see from the dispersion relation on the left here. So I should always, whenever I'm reading the dispersion relation, I should not look at in the y direction, but I have to look at in the x direction. Let's say this is my frequency. So this is omega equal to constant, some frequency. Okay. When I'm in the first medium, my k is here, right? And when I go to the second medium now, with a refractive index of, let's say, n medium here, this is going to increase. So the k is increasing. As the refractive index changes, the k increases. Okay. This is one of the take home I want you to remember. As n increases, the wave vector in that particular medium increases. Okay. So so let us look at it. I mean, this is intuitively what it means, right? The wavelength reduces and the speed reduces. Okay. So we have actually done numerical simulations of this. I mean, this is a very simple numerical simulation, which is kind of a calibrating or rather it's a sanity check. If you, let's say, are running some electromagnetic wave simulation, this is one of the first simulations you would do just to check that, you know, your simulations are correct. So what we did in this case is we took the same interface between, let's say, air and glass. And of course, just ignore, I mean, this, we have to define a finite size boundary. We can't, of course, solve the electromagnetic waves in all space. So we define a boundary. So this is the domain over which we are solving the wave equation. And so the wave is incident in the normal direction. And you see the same, you know, the phase frame, these are a little bit more detailed than what you saw. On the left, you are just seeing a few planes, discrete planes. But here, essentially, you are seeing how the phase changes continuously over a region, right? So these are the phase fronts, and of course the distance between the phase, the periodicity of the phase front is essentially the lambda, right? Let's say lambda air, okay? And it's a normal direction, it's going. Now, when we come into the second medium, we clearly see that the lambda in the medium has reduced, okay? The phase fronts have become closer to each other, okay? And of course, you know, we can define the relation as omega is c times c by ng, which is the slowest velocity, and the wave vector in that particular medium, which is kg. So this is a cross-sectional view. If you actually run, I mean, the domain that I was talking about, it's a three-dimensional domain, and you can see that in the plane perpendicular to the normal in the direction of propagation. So the wave is propagating in this direction. In the plane perpendicular to it, the phase is constant. So these are two cut lines. In essence, we have all of this space will be filled like this, okay? But we just took two lines just to see how the phase is behaving. So the cut lines show that it's in fact a plane wave, and the plane wave, as it's propagating, the wavelength in the second medium has reduced. All right. So now, what happens when you have oblique incidence, right? So now let's consider this scenario wherein I have, let me just, let's say I have a normal direction, and now I have a plane wave which is incident, let's say, in this direction here. Okay, let me call it theta I. What happens? Of course, all of us know this. I mean, we have studied, right, in basic physics, and not sine theta I should be equal to ng sine, let's say, theta g or whatever, yeah, in the glass. But this is not very satisfying. So we want to analyze this in a little bit more of detail. Okay. So for that, let me define the axis. Let me say that this is x direction and this is y direction. Okay. So now I have to generalize. So far, the wave vector we have considered as a scalar. It's a number, right? Just some, but it's in fact it should be a vector because it denotes the direction of propagation. So now, if I have this axis consisting of x and y, what will be my k vector in the first medium? So let me call this as k1, and it should be a vector, and that should be equal to, in this case, okay, I'm going in the negative x and negative y direction. Well, let me hide all the directions in the constant. So let me simply call it as kx, or rather I'll call it as k1x x cap plus k1y y cap. Y cap and x cap denote the unit vectors, and kx and ky, k1x and k1y define there are some numbers. Okay. So what does it mean when you have a vector for the wave vector? Of course, because of vector addition, we definitely know that in this case k1 square, I mean this is air, so this actually is k0 square, right? K0 square, that should be equal to k1x square plus k1y square. Okay, That should be the relation between the k1x and k1y. Now, such a wave is incident on this medium. What should happen? Okay. Well, it turns out that we should have a second wave vector. We don't know what the components are, but I can in general write the second medium wave vector as k2. I can write it as k2x x cap plus k2y y cap. Okay. Now my problem is to define what these components k2x and k2y are. Okay. And to do that, we will use a simple symmetry law, which essentially says that if you the parallel component of wave vector remains constant across an interface. Okay. The reason this happens is if you look at this interface, in the x direction it is infinite. Okay, there is no features. Okay, so because of the symmetry, translation symmetry, it turns out that the parallel component of the wave vector has to be continuous. But when we look at it in the perpendicular direction, we see that the wave is going to hit an interface, right? So there is symmetry breaking here, and because of that, the normal component has to be different. But the parallel component sees essentially there is translation symmetry in this direction, so the parallel component is always conserved. Okay, this is similar to the boundary conditions you will encounter in electromagnetism. We see that the tangential component of the electric field is continuous, and so on, right? All right. So what does it mean the parallel component is continuous across an interface? It means that k1x should be equal to k2x. Okay. So now it kind of simplified our problem. So now your k2 should be equal to k1x x cap plus k2y y cap. All right. But we already know that the absolute value of the wave vector has to increase by n, right, as we go into different media. So essentially k2 is going to be, because the refractive index is higher by ng, so k2 is going to be ng square, and I can call it k1 square. Okay, equal to k1x x cap plus k2y y cap. Okay, so now clearly what we see is that LHS, right? LHS is larger, so automatically this has to increase. Okay, k2y is higher or is greater than k1y. It has to be that, right? Because this first term is same. The only way the LHS will be equal to RHS is when k2y is greater than k1y. What does it mean that k2y is greater? So this is simple vector addition, right? So I can think of, let's say in this case, I'll decompose my wave vector, this is my direction of propagation, right? So I'll say I'll decompose into two components. Okay, this is k1y, this is k2y. When I decompose it that way, I'm seeing that, this is k2x, okay, and k1y. I'm sorry. There is a phone call, so there's a slight disturbance. Just a moment. So yeah, this is k1y, and this is k1x. Okay, and now we saw that the tangential component has to be same, so this also is going to be the same length, but now this is longer. When this is k2y and this is k1x equal to k2x. So it automatically means that the wave was propagating in this direction, now it propagates in this direction. The wave bends, right? And that's why we see that the bending happens this way. This is my theta 2. Okay, and this is a more intuitive or more physical picture of what is happening. Okay, so we have done this. Again, as in the previous case, we have done the numerical simulation just to show you how it looks like, right? Just to satisfy the intellectual curiosity. And as I said, this is a sanity check. Whenever you're running any numerical simulations, especially the electromagnetic waves, these are one of the first things you will check. Check the Snell's law in normal incidence, or rather, how the phase fronts look like. and then look at the Fresnel equations essentially, okay, at oblique incidence. Any problem with the numerical setup will actually cause errors in this, and you will not be able to see proper phase friends. Okay. So now, as we expected, there is this angle of incidence, and the moment we go into the second medium, the wavelength has reduced. You see this? The wavelength has reduced compared to, this is the wavelength in the air medium. In the second medium, we have the wavelength reduced. That means the K medium is higher, which as we expect it should be. And the parallel component is continuous, and because of that, the bending is towards the normal. Okay. In fact, I mean, if you look at the equation, right? I mean, if you look at Snell's law, it is nothing but conservation of wave vector in the parallel direction. Okay. Because we said that K1x should be equal to K2x. Okay. And if I decompose my wave vectors, you know, I have wave vector like this, I can decompose the x and y components. Simply, I know the angle of incidence. So my x component will be essentially K1 sine theta I should be equal to K2 or rather K2 sine theta 2. Okay. So anyway, I know that in the first medium it is K0. So I can simply, I mean, N0 I can put, and then this will be N0 sine theta I should be equal to, K2 is N times higher. So Ng sine theta 2. That's it. Your Snell's law is effectively conservation of wave vector, okay, in the parallel direction or parallel to the interface. So of course, lambda 1 is greater than lambda 2. All right. So this is how you can look at electromagnetic waves. Okay. Now I want to introduce a slightly more complex concept. Okay. That is, we are all familiar with the time and frequency, right? These are essentially Fourier transform pairs, right? Time and frequency, Fourier transform pairs. What we mean by that is, when you have a signal in time, I can define a frequency for that. And if I have a signal which is varying very, very fast in the time, automatically it has a higher frequency. So these are inverse relations, right? So the advantage, the reason we do this is that we know any arbitrary time signal can be decomposed into any arbitrary signal, time signal can be decomposed into harmonics, right? The fundamental sinusoids, right? When you have them, you can essentially construct any signal out of that. The weights, the Fourier, the weight of the linear combination will change. That's it. Okay. Now we want to extend that into the space domain. So what I'll do is, instead of time axis, let's say we can construct a similar frequency or concept of a frequency in the space axis. So this is x, this is some amplitude, let's say a. Okay. Now I can have a signal which is varying in space like this. So I can define a spatial frequency associated with that. Okay. Now let's assume that I have drawn this. Now I have another, just for example, another periodic variation, which is of this form. Let's say in blue, I have this, right? So when I have these two spatial signals, okay, means as a function of position, they are changing. And this could be a simple diffraction grating, you know, simple lines that are drawn, let's say, and you have two media. So there is different, when you have diffraction grating like this, essentially you have a spatial signal. When you have such a scenario, you will see that this, we can define, let's say, some spatial frequency. I mean, it turns out that these spatial frequencies also can be represented in terms of case. Okay, case. Let's say, what I'm saying is, your periodic variation can be constructed as a linear combination of these spatial frequencies. Okay, so let's say if I call it K1, this I'll call it as K1 spatial frequency. I mean, of course, it's not going to be a single spatial frequency. It's going to be a combination of many, many spatial frequencies. But what effectively we can say is, the signal 2, right, on the bottom in the blue here, this has higher spatial frequencies, whereas signal 1 has lower spatial frequencies. Okay, and this is exactly analogous. You know, in the regular Fourier theory, whatever you have, right, the basic harmonics, those are sine waves, right? in electromagnetic waves, these are essentially plane waves. Okay. Now what I have here is a square grating. We call it a grating essentially. Okay. So for example, this could be like, this could be glass, let's say 1.5 strips of glass separated by air, right? This is a grating. So when I have a square grating like this, I can decompose into sum of harmonics, which are essentially plane waves. So in addition to the fundamental, a plane wave we've already seen, right? A fundamental or a simple plane wave is going to have an amplitude which is sine wave like this, right? Whereas if you want a square grating, you have to sum up many square plane waves, right? So you have to have the fundamental, and then you have the third harmonic and the fifth harmonic and so on. You sum all of them up with the appropriate amplitudes, you'll get the square wave, right? So, and this is what is shown here in the pictures. So what you see on the top is there are these variations in the, let's say I call it a grating, okay? Some strips, let's say maybe this is glass, okay? And separated by air, strips of like this. So when you decompose this in terms of spatial frequencies, they turn out to be of this form. What this essentially means, this is a pictorial representation of the spatial frequencies. So you have the fundamental frequency in the center, and there are these harmonics which are actually having smaller amplitude. That's why we are not seeing them. Even if you calculate, let's say the Fourier transform of a square wave in time, you'll see that the first one has certain amplitude, then the amplitude reduces as to go to higher and higher harmonics. And that is what this picture shows you, that you have a central harmonic, fundamental, and then harmonics which are having smaller and smaller amplitudes. Okay. So whatever information that you have here in terms of this, spatial variation of, let's say refractive index is captured by these numbers which are harmonics, and okay. And there's an amplitude associated with those harmonics. Now what would happen if I try to bring these variations, now I have these variations, and by some magic or some kind of fabrication, I can actually, let's say, bring them closer to each other. I'll reduce the distance between the variation, the grating, right? The period of the grating I'll reduce. If I do that, what happens to the spatial frequencies? Well, of course, it's a Fourier transform pair, right? If you reduce it in time, the frequency increases. Similarly, if you reduce the period in space, the spatial frequency increases. So instead of this case, I might have a case wherein, the harmonics are more spaced apart. Okay. So this can be even more generalized. For example, I can take two perpendicular gratings. So this kind of a mesh grid on the bottom. If you look closely, this is essentially two gratings which are perpendicular to each other. So you have a mesh grid. And so now I can have frequencies not just in one direction, but in two dimensions. Okay. So I have the spatial frequencies in the X direction and in the Y direction. Okay. And effectively what this is telling me is all of this image is being captured by this. Okay. You can extend this concept to image processing as well. Whenever you look at an image, we can define spatial frequencies, and it becomes very, very interesting what happens, So you can play around with images just looking at the frequencies that are present in it. Okay. All right. So how is this useful? Well, the reason it's useful is it helps us understand some very, very simple and fundamental concepts that we are all aware, but it just throws new light or a more deeper insight into that. Let's consider for a moment that I have an image. Okay. I have a question here. Yeah. Let me just take the question and then we'll come back. Yeah.
So can we see only the spatial frequencies for periodic structures? Even if we have a single structure, can we decompose them?
Well, yeah, the question was, are spatial frequencies there only for periodic structures, or can we talk of spatial frequencies for isolated structures? And the answer is that let's consider what happens. Are the frequency is the concept of frequency defined only for what happens when you have a delta function? Okay, what happens in the frequency domain? So if you have a function which is an impulse of this form, right? Just one delta function, what happens to the frequency? So all across, right? It becomes infinite in the frequency space, right? So if you have narrower and let's say you have two objects, okay? I'll consider one object of this fashion, and then I have another of this fashion. I can definitely, the Fourier theory assures me that I will be able to find the harmonics, which will help me decompose this into there is no reason why an isolated pattern is separate. Even this pattern can be decomposed into any number of some number of harmonics. And if I consider another signal which is broader, let's say, this will have lower harmonics. Okay, if you compare these two, this will have fewer harmonics. That's it. Okay, does that answer the question? Yeah. All. How do we see these frequencies? Well, okay, if you look at the regular electronics, you can, in oscilloscope, you see the time signal, right? And also oscilloscope has a feature to actually calculate the frequencies. But in the case of optics, it's actually a little bit more easier. We don't need to do any sophisticated any processing. We can take a simple lens. Okay, let's say I have an image. Let's say this grating, I can image a lens, and I can focus on the grating using a lens, and I can look at what is known as a image plane or a Fourier plane of the lens, and I will see the diffraction grating, or rather I'll see the Fourier spectrum or the spatial frequencies. So in the case of optics, it's just a little bit more advanced, but lens itself acts as a Fourier transform. Okay, you can use a lens and look at the Fourier. You can look at the spatial frequencies, and that's why these are actually the experimental frequencies. I picked it up from a manual by Thorlabs. I mean, they have a nice Fourier optics kit which helps you understand various things, and I picked up from there, and it can actually be seen. You don't need to even compute these things. All right. Okay. Thank you so much. Yeah. So let's now go a little bit deeper. So now we understand what is spatial frequency. So let's consider an image. Okay, I'm looking at an image in 2 dimensions. Okay, so in this case, there is a word, let's say nano written. Nano essentially conveying that it's something very small. Okay, much smaller than the wavelength. What happens when I have such an image and I look at it from far? Okay, this is my, let's say, this is my observer. Okay, I'm having this image at, let's say, z equal to 0, and I'm going farther and farther in z direction, and I'm wanting to see what the image looks like, right? I mean, this is something very natural for us. If you have a very tiny object, you go very close to the object and you look at it, right? Because you can see it clearly. But if you go farther and farther, you're losing some information, right? I mean, you don't see it very clearly. That's a very natural observation for us. Okay. Now we want to understand what happens in the context of the theory that we have developed. Okay. So now what I can do is I can define, if I have any object, right? We already said I can define spatial frequencies. It need not be, as the question was there before, right? Does it have to be any periodic functions? No, it did not be. Any random image, right? I can define spatial frequencies in that. So I'll construct, let's say, some kx and ky, because it's a 2-dimensional object. I just need kx and ky. Will capture all the information, right? All the information about the object. In this case, my object is simple image nano. So my kx and ky will capture everything that needs to be known about the object. Just a moment. Okay. So now we also should remember, I just mentioned this already. So let's say if I have x direction in this case, I have 2 objects. Let me say object 1 of this fashion and object 2 which is narrower. Of course, the object 2 has higher spatial frequencies. Higher spatial frequencies. And the object 1 has, this is having a lower spatial frequencies. Now, the question is, what happens to those spatial frequencies, right? So what do you mean you're seeing an object? Essentially, the light from that object, let's say there is some general light, let's say the room light, tube light from the tube light is hitting the object and it's reflecting from there, right? So if you are able to, are we able to capture that? Okay, are we able to see it? So the primary question in this case is, what are the spatial frequencies? It's one thing to have, frequencies of the object. So it's one thing, the object can have any high spatial frequencies, but can we actually see them? Think about it from the electronics perspective, okay? Let's say you have a wire which is used to send electrical signals and increase the frequency of the signal. Can you keep transmitting it? If you have done any simple experiments, with let's say soldering and all that, on a PCB, let's say you solder a couple of components and you try to drive it at, let's say, gigahertz frequency, you will never be able to do that because there is a capacitance associated with that, and because of that, there is a finite there's a finite high frequency limit. Beyond that, you cannot propagate a signal. A similar thing happens. We cannot propagate any spatial frequencies, but we can only propagate spatial frequencies up to a certain point. And excuse me, to understand that, let's try to do this. Okay, let me try to draw. So I have, so like in the previous case, I will draw a kx and ky. Okay, so I don't know what the harmonics are. Okay, but I know that when I have an object like this, I can decompose in the Fourier plane in the as a combination of spatial frequencies. Okay, now what I claim is that when I have a structure like this, let's say, I will draw a certain. I want to do it in, let's say, let's say I will move it. Okay. So what I'll say is, let's say I have a medium, let's say with a wave vector k0. Okay, I can define, I've already said that this is a vector addition, right? K0 square equal to kx square plus ky square plus kz square into 3 dimensions. Okay, so now the question is, what happens? We said what does it mean the object has higher spatial frequencies? That means the kx and ky are larger. That means you have very, very small features. Okay, when you have small features, what happens when kx square plus ky square is greater than, let's say, k0 square? What do you think will happen? Okay, well, from the relation, we can say that kz square is equal to, or rather kz equal to square root of k0 square minus kx square plus ky square. Okay, so now what happens when kx and ky are large? Well, the second term is larger, so the whole kz becomes imaginary. Kz is imaginary. What does it mean kz is imaginary? So we've already seen that, let's say, the information is propagated by various plane waves. Okay, and I know how to define my plane wave. So since the information is propagating in the z direction, in this case, I can talk of a plane wave of the form exponential I k z in the z direction. Okay, so when I have this plane wave, and which is basically propagating, and now my kz is imaginary. What happens when my kz is imaginary? Okay, well, this exponential ikz becomes exponential minus kz and z. Okay, what does it mean? As z increases, as z goes to infinity, the wave decays. Okay, so now what we are saying is, we have the information can be constructed in terms of spatial frequencies, but if you have very large spatial frequencies, those spatial frequencies cannot propagate, they will decay. Okay, that's why in this kx and ky plane, I can talk of all the frequencies which are below, let's say, k0, as I'll call them as propagating waves. Okay, and all the spatial frequencies outside, let's say, the circle. By the way, it need not be just a circle. I can engineer my medium to make it look like an ellipse and so on, but let's ignore that for now. But all the frequencies outside this circle, I'll call it as evanescent wave. Evanescent. There is nothing exotic about it. It's just that evanescent waves mean that as they propagate, they decay over. Okay, it's not, the decay is different from the absorption. Okay, even if you have a perfectly lossless medium, these very, very high spatial frequency waves will decay. You don't need to have an absorption. It's just that the medium is not supporting it. Okay, this is slightly different from the absorption that we talk of in the previous case. Okay, in this case, because of the higher spatial frequencies, the medium is not supporting. All right, is that clear? Is there any question?
If you say that the medium is not supporting higher spatial frequencies,
Mm-hmm.
say if we have like a higher index medium,
Mm-hmm.
will it be supported in that medium?
Oh, well, okay. the question was that we said some k naught, right? The medium, if let's say if you have air has a certain limit, okay, of let's say k naught, right? Some number, and it is not going to definitely support waves which are having higher frequency than k naught, spatial frequency. Now the question was, can we consider a medium with a different refractive index so that the k naught is different? Well, of course you can. Okay, so instead of this, I can draw one more circle. Let's say, let me do it in, okay, red. I'll talk, I mean, the circle is not going to look perfect, but okay, I can define another structure which is, okay, I'm centered around this. So now, if I have a medium with, let's say, this is second medium, n medium is greater than, let's say, n naught, 1, right? If you have such a medium, yes, definitely it will support. I mean, if some of you have, are used to swimming, if you go underwater, actually things look more clearer. The reason is, water has a higher refractive index. Its refractive index is 1.33 compared to air. So when you go into water, you see things clearer. Okay, it's yeah. So you see, these things are everywhere around us, but sometimes we don't notice them. But that's the beauty of science. As you go deeper and deeper, things make sense. I mean, we initially learn them as some sort of laws, but then yeah, there is a reason why those things have to be that way. Okay, and if you keep looking at that and keep asking questions for everything around us, we will definitely understand the fundamental ideas in a very, very deep fashion. All right. So now, yeah. So just I mean, a better answer to the question. So I told you how it is qualitatively, but this is a quantitative answer. Okay. I've taken this book this image from a book by Hohenester. You can see the reference here. So what he did was, he took this image, nano, right, in the previous case, and constructed the spatial frequencies in that. And we already said, I mean, this is what we effectively said, right? This is kx and ky, kx, and this is ky. Okay, you have the spatial frequencies, and these spots are essentially those harmonics that are, expected to be there in that object. Okay, these are actually calculated numerically and all that. So now, when you take this object, and let's say, I mean, I'm now defining this circle k naught as some arbitrary number. Okay, well, I mean, if I take it as, let's say, 5. Okay, right now, you see, you take that and you reconstruct. Okay, so what is done here is, the object is, let's say, I should write it. So the object is reconstructed from spatial frequencies less than such that kx and kx square plus ky square less than k naught square. Okay, you consider only those spatial frequencies inside the circle and reconstruct. Okay, you can do that because, I mean, if your reconstruction is perfect, then you should get the image. Okay, so in this case, when k naught is large, or when the circle is large, you are effectively seeing the same object. But now I reconstruct with smaller number of k's, I mean lower case. I discard the higher spatial frequencies. Okay, so when I reduce my k naught, what I am doing is discarding higher spatial frequencies. Okay, when I discard my higher spatial frequencies, what I see is progressively the image is getting worse. And what this is also telling you is that the high spatial frequencies, okay, of course this high is always a relative word, okay, relative to wavelength, let's say. Okay, I mean rather, yeah, if you have an object which has features that are much, much smaller than the wavelength, it turns out that those are high spatial frequencies. Okay, you can think over it and it'll make sense. Okay, high spatial frequencies define sharp edges. Okay, and low spatial frequencies capture say long distance variations. Okay, long distance in the sense broad strokes, right? Long distance variations. Okay, and this is exactly what you will see in electronics. You take any basic, the first year electrical circuits course, and you take a square wave which is having very sharp edges, let's say high frequency square wave, and you pass it through a low pass filter. What happens? You will see that the square wave, I mean, if depending on what the frequencies you're filtering out, you might even get a sine wave. Okay, that means you are discarding all the higher frequencies, and then you are getting a broad sine wave, right? So, I mean, you can do these experiments, and you choose a low pass filter with a different frequency, higher cutoff, you will see it better. Okay, so this is how the spatial frequencies are a very useful idea in understanding nanoscale objects. Okay, so this is a theoretical aspect. Okay, so I hope you are able to capture, you are able to understand the idea. And are there any questions now? Okay, the question was, what if you filter out the fundamental frequency? Then you get the DC. You don't get any image.
Then keep the higher.
Oh. Okay. Instead of a low pass filter, you use a high pass filter. Okay. The question was, yeah. So what if you filter out all the, you filter out the DC and you also, DC and also the higher frequencies.
Keep the higher frequencies.
Okay.
The higher frequencies and the fundamental is filtered.
Okay, yeah. The question is, I'll use a high pass filter, essentially. So what happens when you have a high pass filter? Think about it from the electronics perspective. What would happen? You should do an experiment. What happens? So essentially, I think you'll only see the edges sharply. If you look at the image, now the image is looking like nano, right? Here, you're actually seeing the white and the blue is the background. When you filter out all the fundamentals, you'll not see the insides clearly. You'll end up getting some, this is my expectation. So you'll see something like this. This is my expectation. N will look like this. So the intensity that is there, all of that intensity is filtered out, right? Only you'll see the sharp edges. Okay, and also remember, the amplitudes are also there. The spatial, it's not just the frequency, the amplitude of it. So effectively, you throw out enough lower frequencies, then you're throwing out the information almost. It's very, very negligible. You might actually find it difficult to see from the background. Because as you go to, let's say, third harmonic or fifth harmonic, the amplitude turns out to be very, very small. So you will not exactly see it. Now the interesting thing will be, I'll take the fifth harmonic and I'll amplify it and see what happens. So then I think you will see the sharp edges. But yeah, this is something that so actually, this is wonderful. Actually, we should actually try to look at this, and I think the book has a toolbox. So I'm not sure if he has provided the code for this, but it might be an interesting thing to verify. Okay. So yeah, if somebody is doing research on this, I'll encourage you to look at this. Okay. All right. So yeah, that is an interesting question. Okay. All right. So yeah. Thank you very much for your attention. This became slightly longish lecture, but yeah, we will continue. In the next lecture, we'll take off from here and we relate it to some very fundamental concepts that we know. All right. We'll see you in the next lecture. Thank you so much.